approximately the same. This is halfway in mass between these guys and these guys because this contains 1 lambda 0 and this contains 2 of them. Now if you make an assumption concerning the energy of interaction, if you say, for example, that when a lambda 0 and a lambda 0 bar interact, that energy of interaction is this, and this is in the interaction of n0 and n0 bar, and you average this, this should be the same as this. So if you make that assumption, then you get the following relation, that the mass squared of the phi is twice the mass squared of the k star minus the mass squared of the rho. And this works extremely well. So this is really quite exciting. This is like what eventually was called the constituent quark model, but it wasn't because I didn't assume any potentials. No potentials were assumed. I didn't think we knew what the potential was, so I tried to find relations that were independent of the potential. Now, since 3 aces made a baryon, an ace had a baryon number of 1/3, and then with this famous formula, these objects turn out to have fractional charges that you're familiar with. And if you combine 3 of them and you ask what their irreducible representations are, you get 1, 8, 8, and 10. And 8 and 10 and singlet representations we're seeing for the baryons. So here's a picture from the CERN report of February of '64, where you see pictures for the wave functions of the ordinary baryons. So here's the proton and the neutron. I got tired of drawing squiggly lines, so these are just the springs that hold the particles together. I said that although I didn't know what the forces of interaction were, I said there were no 3-body forces when I tried to determine what the mass relations ought to be. And the rule that I had, which Murray called Zweig's rule, was that the way in which these particles, for example, this one decayed, was, or the way in which you figure out what the amplitude of that decay is you write down the wave function for the initial states in these terms and the final states, and you see all the different ways you can connect the particles so that the initial aces go to the final aces. And then you weigh each one of these by the coefficient that appears in the wave function. Each of these are called trays. And then you didn't have to know anything about SU3. It would give you all the coefficients that you would get from SU3, but it would give you additional relationships because you, for example, with the non-nets, would combine octets with singlets in very particular ways. So we had in the limit where all these masses were the same, SU3 symmetry, but then the mass differences broke this SU3 symmetry. So SU3 symmetry was this way. Broken SU3 distinguished this mass from these two, and when you broke SU2 and got masses among the different charges, the different charge particles in the multiplet, you get those by distinguishing the mass of the N0 from the P0, making the N0 heavier. So that was the expression for the masses. View of the masses. The interactions really said that it was the aces, not the hadrons, that would interact. So for example, in beta decay, when a neutron goes to a proton, an electron, and a neutrino, it's not the neutron that's beta decaying. It's the N0 in the neutron that's beta decaying into the P0, which is lighter than the N0. So the strong interactions obeyed this rule. The electromagnetic and weak couplings involved not the hadrons, but their ace constituents. So you had gammas interacting again, not with the proton, but with its charged constituents. And once again, if objects underwent weak interactions or weak decays, it was their ace constituents. And this was a lot like what people eventually called the current quark model. So what I call them, concrete quarks, were really a combination of current quarks and constituent quarks plus this rule. Okay, so let me just quickly summarize. The hadrons are supposed to have point constituents. Well, what are the point constituents that we knew at the time? We knew there were leptons. Well, how many leptons were there? There were 4 leptons. So there ought to be 4 aces, and that was one of the reasons that I picked the word ace, because there are 4 aces in a deck of cards. However, there's a more classical explanation for the word ace. Ace actually, if you look at where it comes from as it's used in the deck of cards, actually comes from the Latin ace, it's AS, and it means unit or one. So it's a natural term. So aces were the origin of the SU3 symmetry, but it went beyond SU3 symmetry because it restricted the representations in the quantum numbers. So the baryons came in 1/8 and 10s, these mesons in 1/8 and 9s. But most interestingly, if you looked at the excited mesons, you could understand their spectrum by saying that they had an orbital angular momentum and also a spin, and then a total angular momentum. And the low-lying L = 0 states are the simple ones that you've seen, but there was also evidence for higher angular momentum excitations, and also evidence for L.S interactions. Most interestingly, there was a set of mesons that you couldn't make out of AA bar. So this is a combination of spin, parity, and charge conjugation. These are forbidden. So that was the picture. So this was written up in this CERN report, 80-page report, lots of details. So it sort of looks easy, but it's not as easy as it looks. Because as you may recall, there were 26 mesons that were listed, that were known at the time. This list appeared in the Reviews of Modern Physics. There was a particle data group. This is the precursor of the particle data group. This was the official list of resonances. So out of those 26, there was a division now of 19 and 7. So out of the 26, 19 we now know didn't exist. So only 7 existed. And if you looked at these 19, you could divide them into 12 and 7. And out of these 19, 7 were in this series that were forbidden. So you may ask, well, so the evidence was against it, right? And it sort of looks like it was against it, except there were only a couple of hundred, I think it was something like 250, 230 pages of papers that were written at the time. And I read them all, actually. And I had this training in experimental physics. So I could evaluate these papers. And when you looked at the evidence overall, I think it was clear that this conclusion was unavoidable. And I think basically anybody that had the training and the interest and the perseverance would have come to the same conclusion. Well, what did people think? Are aces real? Well, I didn't know whether they were real, but it was very strange if they wouldn't be real because they had dynamics. What does it mean if an ace has angular momentum and it has spin and it has an L.S interaction if it's not a real particle? So it was very confusing. I didn't know whether they were real, but I sort of thought that they were. Murray really had a different view. When I came back from CERN in 1964 and went into Murray's office and told him about the work that I had done, he listened, and when I was finished, he looked up and he said, "Oh," he says, "the concrete quark model, that's for blockheads." And that was, of course, a very clever thing to say. And that's one of the origins of the term concrete quark model. But you see over here, you see the blocks, oops. You can see the blocks for blockheads. Murray really didn't think the quarks were real. 5 years after the deep inelastic scattering experiments at SLAC, so this is in 1972, this is almost 10 years later, he writes in a paper called Quarks. In these lectures, I want to speak about at least two interpretations of the concept of quarks for hadrons and the possible relations between them. First, I want to talk about quarks as constituent quarks. These were used especially by G. Zweig, who referred to them as ACEs. I would have thought it was more precise to say these were introduced by G. Zweig. In any case, he goes on to say, the whole idea is that hadrons act as if they are made up of quarks, but the quarks do not have to be real. The quarks do not have to be real. And that was also a mischaracterization. He says, there is a second use of quarks as so-called current quarks, which is quite different from their use as constituent quarks. If quarks are only fictitious, there are certain defects and virtues. The main defect would be that we never experimentally discover real ones, and thus will never have our quarkonics industry. The virtue is that then there are no basic constituents for hadrons. Hadrons act as if they were made up of quarks, but no quarks exist. And therefore, there is no reason for a distinction between the quark and bootstrap picture. They can be just two different descriptions of the same system, like wave mechanics and matrix mechanics. So this was Murray's vision, and there really isn't any discussion of this idea of concrete quarks, which combines both the idea of constituent quarks as well as current quarks. I found this quote from Heisenberg. In the early 1970s, the BBC interviewed him, and he was talking about particle physics. And they asked him about quarks. This is basically at the same time that Murray wrote the paper that you had quotes from above. Heisenberg says, even if quarks should be found, and I do not believe that they will be, they will not be more elementary than other particles, since a quark could be considered as consisting of two quarks and one antiquark, and so on. I think we have learned from experiments that by getting to smaller and smaller units, we do not come to fundamental units or indivisible units. But we do come to a point where division has no meaning. This is the result of the experiments of the last 20 years, and I'm afraid that some physicists simply ignore this experimental fact. Well, what did Feynman think? He had no objections to current quarks or ACEs used in the context of currents. Constituent quarks he didn't really like. He thought that the correct theory should not allow you to say which particles are elementary. Zweig's rule he really hated. And every time I would tell him about it, he would get upset. Because he said unitarity mixes all channels that have the same quantum number. And you can't single out rho, phi not going to rho pi. It all mixes. So he was right to really oppose this idea. Because if this idea is right, that in fact you have this suppression, there has to be something unprecedented going on. And he wasn't prepared to accept it. Well, this was it was May of 1968. So this is more than 4 years after what you'd seen before. And I'm walking to the cafeteria, we call it the Greasy at Caltech. I bump into Feynman, and he's very excited. He has just got done teaching a course in high energy physics. He had left the field for a while because he had spent some time trying to quantize gravity and hadn't really been successful. But he decided to get back into the field. And he decided to do that by teaching this course. So he went through and he told me about what he had told the students. And when he finished, he stopped and he looked at me and he said, "Did I miss anything, Zweig?" And so I told him once more about ACEs. And this time he was quiet and he listened. And when I was through, he hitched up his pants and he says, "I'll look into it." So 3 years later, I had already switched to neurobiology, but I still had an office over in the physics department. And I went back to my office, and he had an office in the same building, same floor. And I see him at the other end of the hall. And when he sees me, he breaks out in this tremendous grin. And then I have to put the microphone down. He starts walking like this. It's like this. And he walks right up to my face, like this, and he says, "Congratulations, Zweig, you got it right." So what had happened was that after I had that conversation with him on the way to the Greasy, he started to look at scattering experiments again, and that's when he came up with the idea of partons. He called them partons because he didn't have any reason to believe that they were fractionally charged particles or had anything to do with ACEs or quarks. But then he started to work with 2 graduate students, Finn Ravindal and Marcus Linder, and they looked at photoproduction, photoproduction amplitudes, and finally he reached the conclusion that the idea in fact must be right. Well, there were real problems with accepting quarks. First, for ACEs. ACEs violated the spin statistics theory. You had 3 particles in a state when you made the omega minus. So I knew about this, but I thought it was a little bit like Rutherford's atom or Bohr's orbits. And things weren't working right, but sooner or later they'll get straightened out. The important thing is that you have the constituents correct. It was also like Wegener's theory of continental drift. I don't know if you're familiar with Wegener, but he's the guy that said that South America and Africa at one point were connected. But that idea was not accepted. The evidence was overwhelming. If you looked at the geology, and you looked at the fossil record, there was a clear continuity, but there was no mechanism known to separate the 2. Also, ACEs violated current dogma. They violated this idea of nuclear democracy, which was at the heart of the bootstrap. There were no fundamental particles. The particles made themselves through their own exchange. And it also violated Heisenberg's principle that you only work with observables. Whoever saw a quark. So it was a little bit like Copernicus' view of solar system. You know, it gives you some kind of simplicity, but it really violates the law. Well, in thinking back about whether or not you would have believed in ACEs if you would have been around at the time, I think you would have benefited from using Bayes' theorem. So this idea, which I'm going to explain to you in the context of ACEs, in fact can be applied to judge new theories as they come along. What we want to know is that the probability that ACEs exist, given the experiments. That's what we want. And you can write that in this form as 1 over 1 plus lambda, where this positive quantity lambda is the ratio of these probabilities. So what are these? This is the probability that you could get the experiments if you didn't have ACEs, times the a priori probability that the theory that you don't have ACEs. A priori probability means you don't have any experimental evidence at all. So it's this product divided by this product. The probability that you get the experiments given ACEs times the a priori probability that ACEs exist. Well, the probability that you don't have ACEs is close to 1. If you didn't have any experimental evidence, you certainly wouldn't think that they don't exist. And the probability that you get the experiments given the ACEs is close to 1, because that's how ACEs were cooked up. So this ratio really is just the ratio of 2 numbers, the probability of the experiments, the probability of getting experiments if you didn't have the ACEs, divided by the a priori probability of ACEs. So you accept the idea that ACEs exist when the inequality goes this way. In the Einstein, well, so what does this mean? It means that in the Einstein tradition, I think people would generally think that they could get the experiments without the ACEs. After all, they're theorists and they can do anything. The probability that you have aces is going to be very small. That's someone else's theory. Then you have people in the Rutherford-Bohr tradition, which are more empirical. And I think they would tend to tilt the other way, that the probability that you can explain the enormous wealth of experiments that were known at the time, given that you didn't have aces, was a lot less than the probability that you have these aces. Now, what does all this mean? Because these probabilities are really not measurable. Before I say more about that, let me just say that you always have to make subjective judgments as to what you're going to do. So saying, oh, this is subjective and we don't want to think about it, isn't fair. Because you're going to decide to work on some field or not, or to believe a theory or not. And it's not going to be based on irrefutable evidence. It's going to be based on your judgments. So this is just a way of maybe refining the judgments that you're going to make. The point is that if you're asked at the time, do aces exist? You're going to ask yourself, well, how hard is it to explain the evidence if I didn't have this theory? And then you're going to weigh it against, well, you know, how ridiculous is it to have aces? And you're going to weigh these two factors against each other to decide whether you're going to accept it or not, whether you're going to work on this theory or work on some other theory. Okay, when did acceptance come? While I was at CERN, I got a letter from Linus Pauling. I don't know, Linus Pauling is a chemist. How many people never heard of Linus Pauling? Good. He deserves to be known. He's a fantastic phenomenologist. So he was revising his book on general chemistry. And in the book on general chemistry, he had a long chapter on aces. And he wanted to know whether he got it right. And he got it right. So he saw it was true immediately. I just was in the Soviet Union last year, and I learned that when my preprint hit Moscow, Bogolyubov said this is the way to go. He says, they're real, and he instructed all of his students to work on aces. And those are the students that then, you know, sort of met me, and they were glad to see me and whatnot. And it was just very strange because it was very different than the United States. Russia and the United States are like, or the West, are just like two different universes. And they just go off in their own direction with coupling one way or the other. You can see that in their art very clearly, and you can also see it here in physics. Dalitz, who was a nuclear physicist, accepted aces almost immediately also, because he was used to constituents. He worked on nuclei, he just changed constituents. Feynman accepted aces when he could discover them all by himself in a place that no one else had ever looked for them before, which was in photo production. A lot of people accepted them after the deep and elastic scattering experiments in SLAC. And finally, acceptance really came with the discovery of the psi and the j, which was really the same story as the omega. I'm sorry, the same story as the phi. So it was deja vu all over again, as someone used to say. So, I was at Santa Fe Institute maybe 2 or 3 years ago, and Jeffrey West was introducing the speaker, Chris Llewellyn-Smith. And Jeffrey says, and Murray Gell-Mann was in the audience, says that Murray and I invented aces and they were discovered in SLAC. And so I corrected Jeffrey. I said, no, their existence was confirmed in SLAC. And then we got into some kind of a discussion of whether aces were invented or whether they were discovered. So invention is the product of the imagination, and the discovery is the act of finding or learning something for the first time. So I think current quarks, which are really a theoretical construct, were invented in the Einstein tradition, and constituent quarks were discovered in the tradition of Rutherford and Bohr. And aces contained a bit of each. Okay, if you want to read more, I have a write-up of these lectures. You can go and Google Zweig CERN interview, and there's a link to a paper where this is written out. But I would like to close here by quoting from the conclusion of the CERN report. Towards the end it says, where I'm summarizing things, there are, however, many unanswered questions. Are ACEs particles? If so, what are their interactions? Do ACEs bind to form only deuces and treys? What is the particle or particles that is responsible for binding the ACEs? Why must one work with masses for the baryons and mass squares for the mesons? And more generally, why does so simple a model yield such a good approximation to nature? And then, after listing a number of ways in which one could view the results of the paper concludes with, there is also the outside chance that the model is a closer approximation to nature than we may think, and that fractionally charged ACEs abound within us. Indeed they do. Thank you. Yeah, I'll give you
Questions? Okay. Okay.
I think every student physics will envy your opportunity of being able to talk about theoretical physics every Thursday afternoon with Feynman for a whole year. My question is, did you talk about the paper by Nambu and Erlang?
No.
So you were not influenced in any way, or were you aware of that paper?
No.
Okay.
Further questions?
But were you aware of the paper by Nambu and Han?
Color.
Well, you know, this was, I don't know, 53 years ago or something. I don't remember if I was aware of it. I don't think I was. No. I was
so
not.
about statistics paradox, you were, because you mentioned the, the problem.
Yeah, there was a problem with spin statistics. I did not know about paraquarks or parastatistics.
That was in '65. I mean, what quite early.
Yeah, that was 2 years after this. This work was done at the end of 1963, really.
I guess a related question is, what did you do in 1965? Did you stop? Sorry.
What, what did I do after this?
Because people need to truly, they have to believe in the quark model to work on, try to solve the spin statistical paradox. Right?
Yeah, there was a problem with spin. Look, I did not, I thought whatever the theory of interactions between quarks would be very nonlinear. And I just didn't think I could figure it out. I also thought, and this was more demoralizing than anything else, that even if I could write down the right theory, I would not know if it was correct. And that was very demoralizing.
Anyway, what did you do in 1965? In 64, you were unable to publish the paper, but you returned to the US. Why didn't you try to publish the paper? So something happened to you.
I didn't really care. I mean, it was very exciting. This work was really tremendously exciting. But, I got back and I started to work on other problems. I suppose when I got back to Caltech several months later, I could have gotten it typed up and sending them for publication. And maybe I should have done that, but I just, I didn't do it. I was not allowed to publish the paper while I was at CERN. You had to get permission from the head of the theory group to get your papers published. And he said you could only publish the paper in a European journal. Now, I was there, I had my own support, I had my own publication, I had, I don't know, $1,200 for publication charges and whatever. And he just, so I thought I should be able to publish the paper wherever I want. And he instructed his secretary not to type any of my papers. And, you know, it's 80 pages long. And then my wife is pregnant, you know, and getting a baby. You know, there was just other things going on.
Any further questions?
There's got to be questions.
Who was the theory head at the time?
Van Hove, who became head of CERN, actually. He really, you know, he and Colloquia eventually published a book of reprints of articles on quarks, and he didn't include either of the two papers. I think he didn't like me.
I would encourage more questions, but while we're at it.
Well, there's a question back there. Yes.
May I know why did you choose switch to neuron biology?
The question is, why did I change or switch fields to neurobiology?
Yes. What is the motivation?
That actually goes back, there are many reasons, actually. There are many factors that influenced that decision. When I was in high school, so I was like 15 years old, I read a book by E.T. Bell called Men of Mathematics, which consisted of a series of biographies of mathematicians. Bell himself was a mathematician who later on I found out was at Caltech, and he just used that as a pseudonym. So he knew about mathematics. And the conclusion that you came to when you read this book was that mathematicians did their really interesting work when they were very young, in their early 20s. So I didn't know what the reason for that was, but I thought that no matter what I was doing, at some point, I would just drop everything I was doing, walk out the door, and do something entirely different. Now, I had forgotten this, but after I switched to neurobiology, I actually ran into my roommate in college. And I told him what I had done, and he said, "Oh, that's what you told me you were going to do when you were 15 years old." He was one of my best friends when I was in high school. So that was always there. Then, as I mentioned a moment ago, I didn't think I could figure out what the forces between quarks were. I thought the problem was just going to be too hard. I had seen what people did with water. Water at high enough velocities becomes turbulent. It's very nonlinear. It's very cheap to do experiments with water. You can do lots of experiments. And people still didn't understand really how to think about turbulence. So I didn't think that I could really understand the much more complicated question of what happens when you get matter interacting at high energies. I thought it would be much more complicated than water. Actually, one of the great mysteries is why is it, as it says in the conclusion of that CERN report, why is it that when the theory becomes most nonlinear, when all the energies are low, when you can't calculate anything, you get this extreme simplicity? I think that's a wonderful problem that still really remains to be solved. So, in any case, I just didn't think I could earn an honest living as a theoretician after doing this work. So I had done experimental work. So I decided that I would go off and do experimental work. And at that time, Fermilab was just under construction. This was in the late 1960s. And so I joined a neutrino experiment. There were two professors of physics at Caltech Barry Barish and Frank Scully, and they were running a neutrino experiment at Fermilab. The lab was hardly functioning. There was mud everywhere. I just decided to go there and join their group and see what I could do. And while I was there, I got this idea that you should look for neutral currents using neutrinos. And so I wrote a proposal with Charlie Peck and Frank Scully, which we presented to the scheduling committee at Fermilab. And I remember that after the presentation was over, one of the members of the committee said, don't you have an experiment already at Fermilab? And we had this neutrino experiment. And then we were told, well, this is a national facility. Why don't you go and talk to different professors at various universities and see if you can interest them in this experiment, and then have them come back, you come with them, and make your presentation. And that was it. You know, I'm not going to mess around with this. It's hard enough to do work, good work, if you don't have to, if you don't have to worry about politics. And I just didn't want to get into politics, so I said screw it. Now, the question is, you know, why neurobiology? Because there are lots of things that you can work on. I wanted to work on some field where you didn't know how to think about the problem in principle. See, Rutherford really told us how you think about high energy physics, how you think about physics. If you want to know what everything's made out of, you throw one thing against the other at ever higher energies and see what comes out. You know what to do, you just don't know what the answer's going to be. So I wanted to find some field where you didn't know how to think about things. And biology was certainly a promising area for that. And within biology, there were several possibilities, and I actually spent several years working in different labs. Different professors had their labs to learn what they were doing, how they thought, and finally settled in on neurobiology. Developmental biology was also very interesting, and you didn't know how to think about it. You know, how do you go from a fertilized egg to, you know, a functioning human being or functioning animal? So I picked neurobiology, and I picked hearing because it's the simplest system to study. It's just, the input is simple. Pressure is a function of time at one ear drum. That's all you need. As opposed to the light intensity as a function, you know, at one position, as a function of positions, as a function of color. And if you look at the structure of the ear, the coupling between the units is mechanical. It's fluids, and you can understand it. It's not a neural coupling like in the retina. So I eventually settled in on hearing, and it turned out to be a good choice.
Any other questions?
Well, you've done many things, many different things in your lifetime. Is this piece of work that you are most proud of and enjoy most?
Well, I was actually asked this question by students. And, you know, it happened so long ago. It turns out that recently means like, you know, in the last few months, I solved a problem in nonlinear cochlear mechanics. Nonlinear cochlear mechanics. That's also an area we didn't know how to think about it. I mean, you know that, I don't know how many of you know that there is a structure in your inner ear called the cochlea. And it's a spiral.
What?
Pardon me?
I'm just telling you.
Oh, yeah. Thank you. It's a fluid-filled structure, and when you listen to sounds, waves are set up inside this structure. And when you have a wave, you have a wave equation. And it's a nonlinear wave. And you have a nonlinear wave equation. And so I've struggled for many, many years to figure out what the nonlinear wave equation is. And I have a candidate equation. And so since this is something that I've done very recently, and something that I've worked on for like 40 years, and I actually solved the problem, I think I'm very proud of that person. Now, I may be wrong. I may have the wrong equation. But that's a separate matter.
Feynman and Gell-Mann, which one is your favorite?
No contest.
As I know, Sir Roger Penrose just gave some quantum interpretation on consciousness. So after engaged in neurobiology for several years, did you find any links between quantum mechanics and neurobiology?
Well, no. That's a serious question. I looked. When it's very, very quiet, and you're listening to sound, the question is, does quantum mechanics enter? And I don't think so. What does enter is something that is not very well understood. It's thermal noise. You see, at the threshold of hearing, the transducers in your ear, the things that move and have their motion converted to electrical currents that flow, that eventually end up in the firing of neurons. These parts, these mechanical parts, move less than the diameter of a hydrogen atom. So there's just these incredibly tiny motions. And the question is, how is it that you can detect signals under those circumstances? How can you do that? And I think that's not understood. That's not a question about quantum mechanics, but it is, I think, a very interesting fundamental question. I think people that study vision have claimed that in the process, the rhodopsin molecules that you use to convert photons into neural impulses, that